You know, every time you click your mouse or type a single letter, there's this silent, invisible storm of activity happening deep inside your computer. We're not talking about software here. Nope. We're going deeper to the fundamental electrical magic that makes it all possible. Today, we're going to pull back that curtain on the computer's core. It really all comes down to one big question, doesn't it? How does this box of silicon and metal actually think? I mean, how does it get from just simple electricity to calculating, processing, and, well, creating? That's the mystery we're unraveling right now. You see, at its heart, a computer's design really boils down to solving two huge challenges. First, how do you efficiently move information around from one place to another? And second, okay, once you've moved it, how do you actually do something useful with it? So let's tackle that first problem. Just imagine you've got dozens of tiny components inside a single chip, and they all need to talk to each other, like all the time. You need a system, right? A shared infrastructure, some kind of internal data highway. And that is the common bus system. Honestly, the best way to think of it is like a subway line. I mean, instead of building a direct road from every single house to every other house in the city, which would be chaos, everyone just shares one super efficient subway line. Data from different parts of the chip gets on, travels along this bus, and then gets off at its destination. Simple. So, why go to all this trouble? Well, just try to imagine connecting every single component directly to every other component. You'd end up with an absolute nightmare of wires. It would be a total mess. The bus elegantly solves this by giving everyone one shared path. But, okay, now you have a new problem, traffic jams. How do you manage all that traffic? That's where these special circuits called multiplexers come in. They literally act like traffic cops, deciding which component gets to use the highway at any given moment. And how do those traffic cops get their orders? Well, it's through simple binary signals. Just look at this table. By sending a specific combination of just two signals, S1 and S0, the system can pick out exactly which register gets to speak. A 0-0 signal, that opens the gate for register A. Flip that to a 0-1, and now it's register B's turn. It's a simple, elegant, and just incredibly efficient way to handle addressing. Okay, so we've solved the movement problem. We have our data highway. Awesome, but a highway is pretty useless if there's no destination, right? So now we have to tackle that second challenge. How do we actually process the data? How do we build a calculator from nothing but the simplest possible switches? Well, believe it or not, it all starts with this tiny, ingenious little circuit called a full adder. This thing is the most basic building block of all computer math. All it does is add three single bits together. The two bits you want to add, plus any carry from a previous addition, and it spits out the sum and a new carry bit. That's it. Now, a single full adder on its own isn't very powerful, but the real magic happens when you chain them together. See, the carry out from the first adder becomes the carry in for the second one, and its carry out becomes the carry in for the third, and so on. It is exactly like when you learned to add in grade school and had to carry the one. By doing this, we can build circuits that can add numbers of any size. And this is where the design gets really, really clever. In chip design, efficiency is everything. So instead of building one circuit for adding and then a completely separate one for subtracting, engineers created a single, elegant circuit that can do both. This is a 4-bit adder-subtractor. The secret is a single control wire. Let's call it M for mode. When M is set to 0, boom, it's in add mode. But when you flip M to a 1, a really clever trick happens. The circuit inverts all the bits of the second number and adds 1. This is a technique called taking the two's complement, and it's a mathematical shortcut that, in the world of binary, is the exact same thing as subtracting. So think about it. One wire, one clever trick, and you get two functions in one circuit. That is pure efficiency. But, you know, number crunching is only part of the story. To be truly powerful, a computer needs to be able to manipulate data with surgical precision, flipping individual bits on and off. And this goes way beyond basic math. This is where logic operations come in. They give you incredibly precise control. For example, a selective clear operation can use one number as a template to erase specific bits in another. A mask operation does the opposite, kind of protecting certain bits while clearing out others. And a selective set can be used to turn specific bits on. It's like having a whole set of surgical tools just for manipulating data. So we have arithmetic circuits, we have logic circuits, but scattering them all over the chip would be crazy inefficient.
The logical next step then was to combine all of this processing power into one central, powerful unit.
And that is the arithmetic logic unit, or ALU, the true digital brain of the processor. Here you can see just one stage of an ALU. Data comes in, and then based on some control signals, it gets routed through either the arithmetic circuits we talked about or the logic circuits, all to produce a single result. This quote from the source material just nails the ALU's power perfectly. Because it's one unified combinational circuit, the whole process, grabbing data from one spot, doing a complex calculation, and storing the results somewhere else, can happen in a single infinitesimally small tick of the computer's clock. It is built for speed. All right, so we have this incredibly fast and powerful ALU. But how does it know whether to add or subtract or mask or do any of the dozens of other things it can do? Well, it needs a to-do list. That to-do list is a program, which is just a set of computer instructions. And an instruction is simply a binary code telling the ALU what to do. But here's the revolutionary idea that changed everything. It's called the stored program concept. The instructions, the to-do list itself, are stored in the very same memory as the data they're going to manipulate. And this is a brilliant illustration of how instructions find their data. Sometimes an instruction uses a direct address. It tells you the exact memory location of what you need. It's like saying the treasure is at 457 Maple Street. But other times it uses an indirect address. This is more like saying the map to the treasure is at 300 Oak Avenue. You have to go there first to find out where the treasure really is. It's one extra step, sure, but it gives you a ton of flexibility. And this is how a simple string of 16 bits can become this rich, versatile language. It all depends on the first few bits, which are called the opcode. If the opcode is anything other than 111, the computer knows it's a command that deals with memory. But if that opcode is 111, it's like a switch. It tells the computer that the rest of the bits define a totally different kind of command, one that deals with internal registers or even talks to the outside world. It's a system designed for maximum versatility in a tiny little space. So there you have it, from the data highway of the common bus, to the digital brain of the ALU, all the way to the to-do list of computer instructions. These are the simple, elegant building blocks that really form the bedrock of all modern computing. And as you sit here watching this, just take a second to imagine the sheer scale of it all. Not just one bus, but billions of them. Not one ALU, but millions of superpowered calculators, all executing trillions of instructions every second, all working in perfect silent synchrony, just to bring these pixels to your screen. It's not